Agree with me? There's going to be pk plus 1. And then we have already seen that this sequence is an interesting sequence. It's like M1 bigger than I1. I'm thinking actually. Agree? What we can say about this sequence? Decreasing actually. Okay. And it is going to be bounded.
If the sequence is bounded, parent sequence is bounded, then it's bounded.
Parent sequence is bounded, then it must be bounded, but I don't know that whether it is bounded or not. One thing, do these M1s, M2, M3 exist always?
Maybe
They do exist. Okay? Let me.
Sir, will it be subsequence? Because maybe supremum does not belong to the set. So those terms will not be in the sequence. So it won't be a subsequence.
No, obviously it's not going to be the subsequence of the original sequence, but they will exist.
Yes, they will. It's real.
But let me tell you something interesting. So we are taking basically supremums, but we can take also something that is even more interesting, which is, say, take mi, small mi, to be the infimums of the I where I is bigger than or equal to. Let's define this. Let's say that take supremum of M1, take supremum of M2, so it's bigger M2. So what will be this actually? So this is going to be that, okay, you take this set and take the infimum. And take this set and take the infimum. This is going to be what? This is going to be kind of a sequence where we say that M1 is less than or equal to M2, small m2 less than or equal to M3, so on and so forth. Okay. Clear? What do you mean by equal? You can have equality. You can have, imagine this sequence is just constant values, just like 1, 1, 1, 1, and this is also 1, 1, 1, 1. So the supremums and infimums are going to be same. You can have equality. What would be the relationship of these small m's with these big m's? Will there be a relationship? There is going to be a relationship because the set is same. So I have a set and I have a supremum of a set, the same set, and I have infimum of the same set. So what would be the relationship between supremum and infimum of the same set? The infimum is going to be always less than or equal. So in other words, we are going to say that this sequence of M1 is going to be smaller than or equal. So in other words, I'm going to say that. I'm going to say that I have, kind of, this is less than or equal to, so it's like all this sequence is going on, and then we say that MC is less than or equal to M2 is less than or equal to. That's kind of relationship making. Okay. Now, keeping in view this situation, what you can say about this sequence? So it's increasing and bounded above by. So it must be. And how about this guy? So it must be bounded to by M1, so it must be also convergent by. So we can say that these MI is increasing, so it's convergent actually. So if it is convergent, it must be converging to some number. Okay. MI must be this M sub n is going to converging converge to some number m, and L goes with it. And this capital M n is going to converge to capital M. And goes to. Correct? But M and small m are some numbers. Or if I want to write it more precisely, I can say that this limit n goes to infinity of infimums of I bigger than or equal to n of PI's is what? All this small m. Then this limit n approaches to infinity is going to be what? The supremum of I bigger than or equal to n of Pi is what? Is capital. That are the cases. Now, if this is an increasing sequence and bounded above, so it must be converging to what? Converging to what? In other words, can I specifically recognize this M? And what does this M mean?
Supremum of this.
So it is going to be the supremum of all these M's. It's like it's supremum of one, two, three, and so on and so forth. Okay? And this capital M is going to be what? Be the infimum. M sub 1, M sub 2. So in other words, this M is an interesting number, which is the supremum of infimum cycle. Because all these are what? Infimums. While this capital is infimum of the right. And I would like to define these two numbers as something which we call lim sup and lim n such. Okay. I'm going to call it lim sup. So it's like a limit of the supremums as n goes to infinity of Pn. And we'll call this as lim n where n goes to infinity of Pn, which is basically, so it's like a limit of infinities. The above is the limit of the supremums. Now these two are a very interesting quantity because for a sequence, limit may or may not exist, but these will always exist. These lim sups and lim n's are going to always exist. So it's like if I have a sequence, even though it is divergent, but still you can find an interesting quantity, which is kind of a lim sup or lim n's, depending on that and what is converging to what. And we're going to see that basically that with these lim sups and lim n's, we can have loads of information about the sequence is active. Is it making sense? So I went very slowly so that you can make sense of that why this notion makes sense. Okay? So if I quickly remind what we did, we first of all took the supremums. So it's like supremums of, so like that's a supremum of whole sequence, that's a supremum of the second term of the sequence, and that's a supremum for the third term of the sequence. And since this becomes a decreasing sequence, okay, and bounded by some number, which is shown actually, so this decreasing sequence must converge. And it converges to what? So it's monotonically decreasing and bounded below, so it must converge to an infimum. In other words, we can find such an infimum. And we are giving name that infimum, which is capital R. And similarly, you have the third argument. So I mean, if you see now pictorially what we are doing, I mean, if I say that return back to the picture, and now let me know that what's going on. So you can have lots of upper bounds, but you are saying that among lots of these supremums, which one is the smallest? Which one is the smallest? And you can have lots of lower bounds for the sequence. And then you are going to say that which one is the largest one. And now we can already observe that if a sequence is converging, then what's going to happen? So it's like these supremums are going to come down, then these infimums are going to go up and agree with each other. We're going to prove this actually, that if a sequence is convergent, then the lim sup and lim inf are basically same as lim. Okay. But I'm going to give you some examples in which we're going to see that these exist even for divergent sequence. So let's take an example.
Sir, for a given sequence, are we always able to find its supremum?
For a given sequence, can we find always its supremum? Why not? It may be infinity. We can find it. Therefore, we extend. That's for the reason that we extended the real line. I mean, if something doesn't have an upper bound, then the plus infinity is going to be the upper bound. Let's see that. Because the constant sequence is convergent. So just told that we're going to show that for the convergent is going to stay same. So let's take some examples and let's try to make sense of that. What example should I do? Let's take this example, AN. Something very simple. Okay. So what would be the small capital M1 for this basically? 1. So the supremum is what? It's like a 1/2, 1/3, and 1/4. The supremum is going to be about M2.
1/4.
Going to be 1/2, and similarly I can say that A is what? And then we say that lim inf is what? Lim sup is what? Is basically limit of this sequence. So it converges to what? So what is the limit? K goes to infinity mk. So it's 0, hence
We have already seen.
we're going to say that the lim sup of basically m goes to infinity of Pn is 0. This limb sup is basically limit superior. Sometimes we use word limit superior. Okay. This guy is called limit inferior. Okay. ठीक है. And sometimes for limb sup you also see this symbol at. So instead of so it's like we use this bar, so this is kind of represents and you have a bar over it. So you also note that by basically that's what your limit superior. And for the inferior that's what basically bar below the bar and kind of infinity and approaches to infinity. These are the symbols that are being used for. Okay. How about, can I find limit for this item? So what would be the limits? So what would be the small number?
0.
So the infimum of the whole sequence. How about M2?
Should be 0.
What be?
0.
0 as well. Because the infimum first like 1 half, 1/3 is 0. But if I have infimum of 1 half, 1/3 and 1/5 is going to be still 0. So all these are basically what?
Zeros.
I can show that MK in general is if I take the limits, the limit is going to be for this sequence the n is going to be 0. Okay. But we can already see this instinct observation that this sequence converges to what? 0. And it turns out the limb sup is same. Okay, there is connection between them. Let's explore that connection. Okay? So let's move ahead. Let's do another example. How about if I have Pn negative 1 comma? So what would be M1?
1 sir.
Is going to be 1. Okay. 2. Again 1. So it's Mk is 1, and if you take limit k approaches to infinity, that is 1. Okay. Similarly, small m1 is negative 1. 2 is going to be negative 1. So that mk is negative 1, so that the limit k goes to infinity of small mk is going to be minus 1. Okay. So therefore, this guy is your limb sup. Okay. This guy is your limb sup. Instantly both are different. So we saw that for this sequence, limit does not exist, but the limb sup and limb ends exist. So something very interesting observation.
Right. This sequence is
So give me the limb soup for this basically, limb n for this basically. En equal to say n square.
It won't exist.
and quality infinity.
Positive.
Extended zero.
So the mk
Positive
is going to be what? It's going to be
quality
infinity, and obviously the
Sorry.
limit is going to be, first side is going to be the limb soup and limb n for b and phi both have same.
Yes.
What is going to be the limb n?
Would be same.
There is a
Okay. The limb n is going to be an instinct. It is going to be plus infinity, but it is going to be due different reason. Here we say that since all these supremums are directly infinity, so therefore the limb soup is infinity. But just think about it. What would be the mk?
1. No, M1 would be 1.
mk is that it's a sequence which begins from k squared, then k plus 1 squared, k plus 2 squared, and so on and so forth. So what would be the infimum of all these?
is
MK square.
K.
MK square.
So it's going to be k squared. And for this k square, if I take limit, what it is going to be. That's good. Then and then soup are both same or this is. Okay. Now let's think about some of properties of this result, this notion, this definition actually. And the lemma says something. So it says that suppose I have a sequence AL of real number where the limb soup of this sequence an as n goes to infinity is a number L. So in other words, it always exists. And the limb nth of this sequence an always exists and it's smaller than L. Okay. Then for every for epsilon positive, any epsilon positive, there exists and one and 2 such that n minus L is less than epsilon for all n bigger than or equal to f1. And n minus L is bigger than minus epsilon for all, not for all, but for infinity many. Infinity many n bigger than or equal to what? And what? Okay. And similarly, so it's not for all, this is something interesting. Because if it be for all bigger than or equal to, and to the A and L are going to be basically, L is going to be what? It's going to be the limit of this equation. Because then you're going to say that, okay, A n minus L is smaller than epsilon and bigger than minus epsilon for all n bigger than or equal to. But we know that the lim sup and lim enf are different from limits basically. They can agree with the limit provided sequence is convergent, we can prove it, but they are different. Okay. So in other words, this inequality holds for all n, while this inequality holds for after n1 it holds for infinity many, but not for all n.
सर डबल इक्वलिटी जो डबल इक्वलिटी है वो तो मुझे बता दिए कि a की लिमिट l है l है
एब्सोल्यूट वैल्यू नहीं है ना a minus a log minus
In other words, I can't say that an minus L is less than epsilon and bigger than minus epsilon
Yes,
for
sir.
all n bigger than or equal to n1.
एक true है एक
So in other words, this is true for all n1,
but this
but this part is not true for all. It's just for true for n. Because if it will be true for all n bigger than n, then that's just the limit. That's all. And similarly, you can have a claim about like if then what will be this that what will be that relationship for n minus small l is bigger than minus epsilon for all n bigger than or equal to n2, and the same is less than epsilon for infinity many infinity many n bigger than or equal to. That's what. So let's write a quick proof for that before. You're going to see that this information, this level is going to be an important level for proving the next proposition, which is going to be a very interesting proposition. How should that be? So we know one thing, that this L is nothing but the limit k approaches to infinity, it's mkx. I hope that we all already understand that what I mean by that. Okay. Okay. Now, if I consider mk minus L, what we can say about this one? So, in other words, I can say that this is less than epsilon for all n bigger than or equal. For all k bigger than or equal to 1. Bigger than or equal to L. We're going to say that for a given epsilon positive, this is going to be true actually. Okay. We call that what is mk? So mk is the supremum of ak plus 1 and so on and so on. So one thing that I can immediately say that ak is less than or equal to this supremum mk. Okay, and from this inequality I can derive that this is less than L plus epsilon. Agree? Yeah. And this is going to be true for how many? For how many? This is going to be for all k bigger than or equal to. Is it making sense? So if this is the case, have we got something that we wanted actually? The first inequality. Trust me. Because you know I can throw this on another side and say that AK minus L is less than epsilon. Or K bigger than or equal to. Agree? I like to think of